Alright, let's try to look at how an object orbits. So the best way to think about orbiting is to start by thinking about someone throwing something straight off a cliff. So they horizontally launch something off a cliff of height, let's say 5 meters. What would happen? Well, we know the time that we have is the free fall time. So our time in the air is going to come from the fact that y final is equal to y initial plus v initial delta t plus 1/2 a delta t squared. And y final is 0 because it's going to hit the ground. Y initial is our 5 meters. The projectile has no initial speed in the y because it's going in the x, so this is vx. And then we have plus 1/2 of our negative 9.8 delta t squared. So we move this over, we have negative 5 equals negative 4.9 delta t squared. Divide this over, we see that delta t squared is equal to 5 over 4.9. And so if we take the square root, this is about 1 second. It's a little bit over a second. But we'll treat it as, so this turns out to be that delta t is about 1 second. When we throw it, if we throw it at an initial speed at 10 meters per second, it has 1 second, it will land 10 meters away. And if we throw it at 20, it lands 20 meters. If we throw it at 30, so forth and so on. And the faster we throw it, the farther away this falls from our cliffside. Now what gets interesting is if we start throwing faster and faster and faster, and we throw fast enough, what's going to happen is the following. If you can throw fast enough, the Earth is a curved surface. So if you're standing here and you can throw fast enough, what will happen is due to the curvature of the Earth, 1 second later, you would be back to your 5 meters if you could throw fast enough. So the idea is that the ball is falling, but if you could throw fast enough, 1 second later, you've fallen, but you're still now 5 meters off the ground. So then what happens? You now have 1 more second to fall, right? And you move, and a second later, you've fallen, but because of the curvature of the Earth, you're 5 meters above the ground. And you keep falling like this. You're always falling towards the Earth, but because you're traversing a large enough distance this way in the x, you come to the point where a second later, you're 5 meters back above the ground because of the curvature of the Earth. The speed needed to do this, your speed, it's about 8,000 meters per second. So if you're traveling at roughly 8,000 meters per second, your curvature would match your speed, would allow you to continuously fall around the Earth. And that's what an orbit is. An orbit's when you're constantly falling around the Earth. But you just never quite get there, right? You move and fall, and you're just constantly falling back to the Earth, but you never quite make it. And that occurs at about 8,000 meters per second. Once it's out here moving, the only weight it has, the only force acting on it is the weight. And so when we sum towards the center, we see the sum of our forces is equal to mv squared over r, right? Because we're summing in the radial direction, because now we're following a curved path. The only force is the weight, so we see that mg equals mv squared over r. So we can cancel our m's, and we see that v squared for an orbit, this is v for the orbit, is equal to g times r. And in this case, if we're here, this is roughly what? R then, this is roughly the radius of the Earth. So the speed needed to orbit goes as v squared goes as gr, or in this case, it's v equals the square root of g times r. And if we wanted to orbit higher up, so this is v orbit. And if you wanted to orbit higher up, what you have to do is the following. So let's say this is the Earth, this is the radius of the Earth, and you need to orbit 100 kilometers above the Earth. Well, your new radius out to here, this new capital R, is the radius of the Earth plus 100. So whenever you want to calculate your orbital speed that you need, you just take into account the fact that you're the radius of the Earth plus some distance above the Earth. So in that case, your v of your orbit is the square root of g plus like your re plus 100. Now, of course, with these speeds that we're looking at, we're assuming that we have no air friction, right? If you have air friction, then eventually what happens is you don't have the speed. If you don't have the right speed, you would, if you had friction, eventually this would fall back into the Earth and crash into the Earth, right? And that happens with satellites and other things. Up in space, even where like the International Space Station is, there's still a little bit of air friction, so they're constantly having to do maneuvers and thrusts, and they have to constantly adjust for the fact that they're slowing down every now and then, so they have to make what's called corrections to make sure that they stay up in orbit. And so do satellites. Satellites have so much time up there, and eventually they just don't want to pay for the corrections, or the satellites die out and they burn back up into the atmosphere. Actually, that's the problem that the Chinese space station, Tiangong-1, I think, it's going to burn back up because it's going to not be able to maintain the speed necessary for the orbit. So this is the speed that you have to maintain to orbit. If your speed falls below that, you have two choices. You either need to boost your speed back up, or if you go to a different orbit, you can have that different speed and then you'd be okay. But the idea is that you need a certain speed to maintain an orbit. And the other thing that's interesting about orbit speed, at a given distance above the Earth, it doesn't matter if you want to put my marker or the school bus into orbit, the orbit speed at a given distance is independent of the mass. So this is just some kind of orbital basics on how you can get something into the speed needed to get something into orbit.